Hello, welcome to the learning the using Wavelet in Python. I'm Kazem from codewithkazem.com. In this tutorial, I will show you how to use Wavelet in Python. In this tutorial, I will use the PyWavelets toolbox for applying and using Wavelet in Python. This library is one of the best library for using Wavelet in Python. At the first step, you need to install this Wavelet in your Python. If you refer to the document of this library, this package, if you use Windows, Macintosh, or Linux operating system, you can install this Python package easily with using this uh, command. Or if using the Anaconda Python distribution, you can use this command line for installing the PyWavelet toolbox. As you see in here, because I'm using Anaconda and the software is Spider in Anaconda, I use the conda install PyWavelets to install the PyWavelet package in Python. For installing this package, you need three other packages. You need Python greater than 30.5 or 2.7 or NumPy bigger than this version, and Cython for Cython greater or equal to this version. For displaying the output of some command, you need the matplotlib, and SIP is available for if you in some example if you use the FFT, you need to import the SIP. So for using the example and the sample code for this package, you need these 5 packages to run your Python code. If you go to the GitHub page of this package, you will see that 36 contributor cooperate in this package, and 100 more than 100 commits used for in this package, and you can find some useful things about this package in here. PyWavelet is a free open source library for Wavelet transform in Python. It supports the 1D, 2D, or ND forward and inverse discrete wavelet transform, and the multi-level discrete wavelet transform or inverse discrete wavelet transform. It also supports the one-dimensional and two-dimensional stationary wavelet transform, and it also supports the one-dimensional, two-dimensional wavelet packet decomposition and reconstruction. It also supports one-dimensional continuous wavelet transform. It also supports 100 built-in wavelet filter for custom wavelets, and it also supports the MATLAB wavelet toolbox. It means that you can export or import data between the Python and MATLAB. If you user of Anaconda Python distribution may wish to use the pre-built Windows, they can use this command for installing the pre-built Windows binary from the conda frag channel. This can be done via this command. After installing, after successful installation of this Python library, you can use this command. If you use this command and you don't see any error, it means that you installed this package successfully. After installing the Wavelets, you need to create a wavelet variables or wavelet object. In this course, we will speak about the wavelet objects. How we create a wavelet object. Wavelet object is the basic building block in working with wavelet in Python. You create wavelet object, then you can apply wavelet to the input signal. The input signal can be one-dimensional or can be two-dimensional signals. For getting familiar with different type of wavelet, this Python library support a command. At first, we must import the PyWT library. Then I want to print the different wavelet library or families. Okay, I save the code and run it. As you see, this Python library support these type of Python families. Every family contains some wavelet types. For example, HAR is one type of Python family, DB or Gaussian, GAUS or Mexican hat or MexH or another type of Python family that this library supports. Every wavelet family contains some subfamilies. For printing the subfamily in wavelet, I want to print all the sub wavelet in a family. So I write a for loop. In this for loop, I want to for on the different type of families, wavelet families. I will print the at the first I will print the name of the family. In here is the variable of the loop, the family. Then I will print a separator. Then I will write the P W Y W T dot wavelet list and in the parentheses family. In this way, it will print. I will comment this line and run again the code. As you see, the Python will print the all the Python that this package support. In the HAR, it's just one type of Python wavelet. In the DB family, we have a DB1 to DB38. In the S-M contain S-1 to S-20, and in the Gaussian, Gaussian 1 to Gaussian 8, and another type of Python family. After getting familiar with the supported type of wavelet in this package, we will start to create a wavelet object in here. There are two types of wavelet object in here, discrete and continuous. Discrete wavelet created from discrete wavelet transform. The HAR is a discrete wavelet transform, then I can use it for creating a wavelet discrete, or another wavelet family that is for continuous wavelet transform. I can use it for continuous wavelet transform. Okay. I consider the name of the wavelet object as a W, and again we write PYWT dot and write the wavelet, and in the parentheses you must consider what type of wavelet you want to create, what type of wavelet object you want to create. Suppose that I want to create a HAR, then I write in here HAR. Save and run again. We can now see the W. As you see, W rate is a type of wavelet. The name is a HAR, and it is a filter bank of wavelet HAR. Or we can print the W. When you print a object, a wavelet object, you will see what's the name of a family name, the short name, the length of the filter, if filter is orthogonal or bi-orthogonal, what type of symmetry, asymmetrics, and the discrete wavelet transform true, and it shows that it is a discrete, it's not continuous. It is a continuous, false. It is not a continuous wavelet transform. We can change it, and for example db2, if I change it to db2 and again run the code and print the W, as you see the family name is W's, short name is db, filter length in here is 4, orthogonal true, orthogonal true, symmetry asymmetrics, dw2, yes, it is a discrete wavelet transfer, it's not continuous wavelet transfer. Okay, and now we create a discrete wavelet object. How we can create a continuous wavelet objects? Okay, for creating a continuous wavelet transform, I change the name of the first value to W1 and then WT to again bars equal PYWT dot continuous wavelet, and we create a continuous wavelet as a type of Gaussian. For example, Gaussian 2. And if you run again the code, you can see the excuse me, I forgot the name. It was PYWT, and run it. And if I print the W2, W2 is a continuous wavelet, Gaussian 2. Family name is Gaussian. Short name is GIUS, symmetric, yes, symmetric. DW2 discrete wavelet false, as you said before, it is a continuous wavelet. When the continuous wavelet CW2 is true, it's the complex CW2 false. It is not complex. The output, as you say, when you apply a wavelet to a signal, the output can be complex. It can contain real and imaginary part, but here it shows that this wavelet transform doesn't have a complex output. Okay, in this section we get familiar with how creating the wavelet object. One of the most important things in wavelet object is a filter bank. Filter bank contains the coefficient of a wavelet transfer that is saved in a wavelet object. In the before, I print the wavelet object and you will see the different properties of a wavelet transform. But if I just print the display the W2, you can see it's print that is a continuous wavelet transform. And if I put a variable in here, you can see the different properties of a wavelet transform. For example, a lower bound, number, rectangular or true or false, upper bound. The properties of a wavelet, continuous wavelet, and the discrete wavelet is different. If I bring the properties of W1 that was a discrete wavelet, you can see that the properties of W is different with properties of W2. And the most important thing is here is filter bank. Filter bank contains the important coefficient of a wavelet transform. So the filter bank contains the four filters coefficient. The four filter coefficients are I put w dot declaw. It is a decomposition filters value, low decomposition filters value. If I dec high, it is a high decomposition filters value, and reconstruction low, it is a reconstruction filter value, low reconstruction filter value, and HI, it is a high reconstruction filter value. The filter bank contains all of these variables. Decomposition filters value low, decomposition filters value high, reconstruction filters value low, reconstruction filters value high. There are another properties in W1, as you see here. For example, the family name is a family name rectangular true or false. Is it true or filter branch? See, get filters coefficients. Uh, Return the method that you can use for getting the filter coefficients, or numbers. It is the number of level in these wavelets, or another properties that most important are filter point, that we need the filter points for applying the wavelet transform to a signal. In this section, I want to teach you how to create a custom wavelet object. Suppose that you want to create a wavelet transfer function that is not available in this toolbox. How to create a custom wavelet function? At the first, you must import the pywt. Then you must define a variable. This variable contains your filter points of your wavelet function. As you see here, I create a matrix for filter points. In this matrix, I use sqrt. So I import the sqrt from math library. So you just need to define the filter points variables. As you see here, if I run this and I open the filter point, as you see here, the filter point is a 2 in 2 matrix that contains some numbers. These numbers define your wavelet transform, your custom wavelet transform. After defining the filtered points values, you just need to define, suppose that I want to, my new variable is a wave. In the previous lecture it was W1. No problem, the name of the wavelet object is not very important, it is customized. So my wave equal pywt dot wavelet, as you see here. Then you define a name for your wavelet. In here, because this my website is code with Kazem, I'm Kazem. I define the name of my wavelet, Kazem wavelet. Then you define a option filter underline bank equal. Then the name of the filter branch value, as you see here. If you run this code, you can see if I open my wave, as you see here, the name is Kazem wavelet and the value of the filter branch is as you define it here. If I print this wavelet object, you can see that there is no family name here. Wavelet, Kazem wavelet is the name of the variable. We can see Kazem, for example, Kazem. Then I run again it and print. As you see here, wavelet name is Kazem, and there is no family name here, there is no short name here. Virtual length is 2, is a length of this variable. Orthogonal false, orthogonal false, symmetry unknown. DWT is true because you define some discrete value for your wavelet transform. For defining another variable here, you can use my wave dot. For example, family name. You can define a family name for here. For example, code cousin. The family name. It is just for example. Okay, some type of attribute is not writable. We can just define, for example, rectangular, true or false, true. Or we cannot define all the variables in custom function, just some attributes of our wavelet. Or another attribute, rectangular, we can say true or false, false. If I print again, my wavelet, as you see here, rectangular is false and rectangular is true. Symmetry, you can define this attribute of your wavelet transfer function. In this section, I want to speak about the wave method. The general form of using this function is wavelet wavefun. Inside parentheses, you set the level. The purpose of wavefun method is used to approximate a scaling function and wavelet function. As we know, we have two functions in wavelet. One of them is scaling function and another is wavelet function. For approximation of this function, we use the wavefun. Wavefun is used to approximate a scaling function and wavelet function at a given level of refinement. This level of refinement determines the accuracy of approximation. For using wavelet font, it's very simple. You just import the PYWT, then you define the wavelet object. You learn it in the previous lectures, previous sections. Then for orthogonal wavelet, since 3 is the orthogonal wavelet, for orthogonal wavelet, the wavefun return two functions. One of them is the scaling function and another is the wavelet function. If I run this code, you will see that we have a vector. This vector is calculated based on the Sims 3 wavelet at level 5. It has a 160 element or PSI. PSI is another variable It contains 160 elements. All of them are float. So if you need to approximate a scaling function and wavelet function at a given level of refinement, you use the wavelet function. For not orthogonal or b-orthogonal wavelet function, we just define in here I define a new wavelet BR 1.3. W2 is a wavelet object for this wavelet. At here I approximate this wavelet at a level 9. If I set this level to 3, the most important here is that when you just let me to run this code and print W2. As you see, W2 was here the wavelet object. The orthogonal is here false, and B orthogonal is true. In here, the wavelet function return 4 variables for us. A scaling function for the composition, and a wavelet function for the composition, and a wavelet function for reconstruction, and a wavelet function for a reconstruction. So when our wavelet is not orthogonal and it is b-orthogonal, the wavefun return 4 variables for us. And as you see here, when the level is 3, the size of the R14. But if I increase it to 5, for example, and run again the code, as you see, the number of elements is 160. So when you increase the level of your wavelet, the number of elements in the output of the scaling function and wavelet function is increased. It shows that the accuracy of your approximation increases. I prepared a figure for you. In this figure you can see the 4 sims wavelet function. When the level is 1, as you see, the accuracy of the wavelet function is low. But when you increase the level from 1 to 4, the number of points is increased, and the accuracy of the wavelet function is increased too. So, for having a better wavelet function and scaling function, you must increase the number of level. But when you increase the number of level, it has a direct relation on the level of your speed of your code, because your code needs a lot of resource for computation. As you see here at the level 9, you have a 200 elements in your vector, and this vector needs a lot of memory for computation. So you must do a trade-off in here between the and you cannot set a very large value for your level, and you cannot set a low value for your level because your accuracy is decreased. So you must select an, a number based on your code. You must pay attention to your code and select a good value for your code. One of the best websites for getting familiar with different type of wavelet is wavelets.pybits.com. This website is a Wavelet browser. This website is coded by PyWavelets. In this website, you can see the different wavelet families. In the right side, PAR, WTO, SIMS, Wavelet, orthogonal, reverse orthogonal, but discrete Mayer. If you click on one of the right side, you can see the sub wavelet family. For example, heart just have a one sub wavelet family. As you see in the left side, you can see that this wavelet is a heart. It's a family from heart, properties asymmetric, orthogonal, and biorthogonal. The orthogonal, so it has a two function, scaling function and wavelet function. In the here you can see the coefficients of this wavelet transform, or you can go to the next wavelet family and click on here. You can see that it is for DB4. It is asymmetric, orthogonal, and biorthogonal. It is the orthogonal, so it has a two function, a scaling function. It is a scaling function of this wavelet, and it is a wavelet function of this wavelet function, and it is a coefficient, discrete coefficient. It is a decomposition low pass filter, and the coefficient of decomposition high pass filter. And here you can see the reconstruction low pass filter coefficient and reconstruction high pass filter. If you want to see the value, if you click on here, you can see the value of these red dots in here, or the coefficient of this wavelet. If you want, you can copy. If you click on here, you can see an editable section and you can click it, or you can see the coefficient of the composition low pass filter or the composition high pass filter, and reconstruction low pass filter and reconstruction high pass filter. You can go to the next, for example, DB11. It is a shape of scaling function, and it is a shape of wavelet function, and it is a coefficient of the composition low pass filter, the composition high pass filter, and you can go to the bring example from orthogonal. As I said before, when you have a orthogonal, it is a not orthogonal wavelet. BOR 2.6. It is symmetric. As you see, it's symmetric. If you put a line here, this side and this side are similar to each other, so it is symmetric. The orthogonal. When it is orthogonal, we have a four function here. One function, decomposition scaling function, and reconstruction scaling function, and the decomposition wavelet function, and reconstruction wavelet function. And in here you can see the coefficients for the composition low pass filter, the composition high pass filter. It is symmetric too. And reconstruction low pass filter, reconstruction high pass filter. And in here you can see the for your approximation or TM is break. It is orthogonal, so we have a two function, scaling function and wavelet function. And it is a coefficient. If you want to see the value, you can click in here. It has more than 60 values, 61 values. It has its values. We click its values, value it. You want to copy, you can click on copy. We don't want, click again. So on this website you can get familiar with a different wavelet family that is accessible in this wavelet toolbox by wavelets. In this section we start the main function that is used in this library. In this section we want to apply wavelet to a input signal. For example, in here I have an array or a list. It can be a signal that you can read from a file, or you can read from a microphone, or you can read from output source, or you can read from a audio file in your computer, or you can read from Excel file. It is just, for example, in here we have x equals 3711 minus 2546. I want to apply wavelet transform on this input signal. For applying wavelet transform to the input signal, we use you import a PyWT as you see before. By wt.wt x and the type of the wavelet transform that you want to apply the input signal. You can put here, for example, I put here sims 3, or you can change it to the har, or you can change to the another type. If I save it and run the code, you can see in here I have x, the input signal. It is the 8th element. It's a type of integer, and I have a wavelet coefficient Ca and Ca. As you see here, it is a float and it has 4 elements. Or I can apply since 3 to the input signal. As you see here, the length of the wavelet coefficient depends on the type of the wavelet. In here I have a 6 element for Ca and Cad. Ca and Cad, you can see the value of Ca and Cad in here. After applying the wavelet transfer to input signal, we can apply the wavelet, inverse wavelet with IWT. IWT is used for inverse wavelet. The input is clear. You must get a wavelet coefficient as input to the IWT and the same wavelet type as you used before. Then the output I have Y. Y is the inverse wavelet transform of X. Let's save the code and run it. It was x and it is a y. As you see here, the value of x and y are same. It means that the inverse wavelet transform works fine for us here. In real application, we don't use we extract the wavelet transform and apply the inverse wavelet transform to give the input signal. In here, between these two commands, we use some algorithms or methods. For example, if you want to remove the noise from the input signal, there are some methods, for example, thresholding. You set a threshold, and when, for example, you can set a value lower than 0, you can convert to 0. For example, the fourth element in here convert to 0, or for element in here convert to 0. Then you apply the inverse transform to give the inverted signal from the input, or it is for some application. For example, we have a third type of thresholding, semi-thresholding, low thresholding, and you can find the equation for this thresholding in the paper reference. Or in some application, they want to use it for classification or pattern recognition or detection. After extracting the wavelet transform, they want to use it for input to a classifier, for example, artificial neural networks. So after extracting the wavelet transform, they can apply them to a classifier. But sometimes the size of the wavelet coefficients are very large. For example, 50,000, and you cannot apply them exactly to the input of a classifier. In these situations, we can use some mathematical formula for a feature extraction. For example, some person use variance of the wavelet coefficient or standard deviation, or this formula, for example, angular secant moment, contrast, correlation, sum of squares, inverse difference moment, sum average, sum variance, sum entropy, difference variance, difference entropy, information measures of correlation 1, information measure of correlation 2, maximal correlation coefficient, as you see here. So it depends on your application. If you want to extract the wavelet coefficients from the input signal, you can apply them to a classifier, or you can extract some mathematical measures from the wavelet transform. Or if you want to for example, remove noise from the input signal, you can apply some thresholding or some other your proposed method on the wavelet coefficient, and inverse the result wavelet coefficient to inverse wavelet transform, get inverse wavelet transform from the your wavelet coefficient to get the inversed. So it depends on your application how to use in here. We just here bring a simple example. You can change the wavelet type, for example, r, and again x and y. As you see here, the value of x and y are same. In the previous lecture, we learned how to create wavelet objects. For example, in here, I create a wavelet object from since 3 wavelet. In this section, we learn how to apply a wavelet object to the input signal. It is our input signal x. I want to apply this wavelet object to my input signal. It's very simple. You can just use the pyt.wt and your input signal and wavelet equal to the name of your wavelet object. For example, my wavelet object is W3 in here. You can see what we call them W3, and in here what we call them WT again. Or you can do A. In here you can see A. The name of your object value. So if you apply, you must import pyWT, save, run. As you see, the wavelet coefficient is extracted. So it is a way to apply a wavelet object to the input signal. Or there is another option in here. It is a mode. When you apply a wavelet transform to a signal, because as you see in this figure, the black is a simple example for our input signal. For example, in here I have a 2-dimensional signal to the image, and this is our wavelet filter bank. As you see here in the border of your signal, there is no value for the filter bank, so we must set a mode for these empty values. If I set the 0 in here, the Python will set 0 for border of the signal. PyWavelet provides several methods of signal extension that can be used to minimize the negative effect of non-value in the border. For example, 0 or 0 padding. In this mode, the signal is extended by adding 0 samples. The default mode is symmetry. This is CAD. If I run again the code and we compare the two CAD with each other, as you see, the border value changed, but the middle or another value except the border, there is no change in this value. Or you can say constant. Constant border value are replicated. It is a 4, and 4 is replicated in this value. In when you set 0, all these values are 0, but when you use constant, 4 is replicated to these empty cells. If you use symmetric, signal is extended by mirroring samples. For bigger, because in here I just have a 4 is replicated, but when the size of the wavelet filter branch is bigger and the input signal is bigger too, you can see the difference between symmetric. If you go to the document of pi wavelet, in this document you can see different type of method for signal extrapolation. Zero, constant, symmetric, reflect, reduce, smooth, antisymmetric, anti-reflect. For every method you see example in here. X1, X2 to Xn are our input signal. In add 0 to the order of input signal, but in here constant is for that value replicated, x1 is replicated for another value, xn is replicated, but in a symmetric it works as a mirror, that the value in the right side is replicated to the left side, x1, x1, x2, x2, xn, xn, and minus 1, xn minus 1, and reflect, and you can see the other method that this library support. So for extracting the wavelet transform with wavelet object, you can use the PyWt input signal wavelet equal the name of your wavelet object and the mode. The default is symmetric. Symmetric is a default. If you want to change it, you can change the mode of your wavelet transform. There are some tricky notes about using inverse wavelet transform. You can use noun as a one of the input to this function, as you see here IWT. This one input is a vector and another input is a noun. It is possible that you just apply one input to your IWT, or you can use another output als 0 value. The length of the two vector must be same, but one of the input can be 0, or you can put the first input as a noun and second input as a vector, or you can set the first input as a 0 with the same length as the second input, but you cannot use all to input noun. It is not possible that how do you want to get inverse transform from what? You have there is no value in here, and you cannot, the length of your input cannot be different. The first input has a length is 5, but the second input, the length of second input is 4. You cannot use this case command in this uh, library. When doing the IW transform or inverse the discrete wavelet transform, the coefficient array must be the same size. Only the one argument can be known. No, all of the argument cannot be known. One argument can be known, and you can set one of the input as a noun. You cannot set all of them as a noun. It was some note that you must be now when using this library. In this section, I want to speak about how to do multi-level, one-dimensional wavelet transform or multi-level decomposition using the wave deck. Wave deck, as you see, deck is a variation of decomposition. When you want to do multi-level discrete wavelet transform and find the multi-level decomposition of your input data, you can use the wave deck command in this library. Using this command is very easy. You just need to import the PYWT, then define your input signal and define a variable for your output. In here, I set the name of the output value as a coefficients, COFFS equal to PYWT dot myDeck. First input, then the type of your wavelet, and you define the level in here for the composition level. Level must be bigger than 0. You can ignore the level, and the level will be determined using the DW2 max level. I will speak about it in the future lecture. If you run this command, as you see, coefficient is extracted from the input matrix. The most important things here is that the size of the coefficient is half of the input signal. The input signal, the size is 8, and the array size in here is 4. It is because that, suppose that the left side is our input signal, it is the blue is our input signal. When you apply the wave deck at the level of 1 to your input signal, the new vector has a size of 4, as you see here. So at the level, if you apply the level 2 to your signal, the remainder is 2. The size of the output coefficient, the size of coefficient of your Wavelet transfer is 2. And if you apply the level 4 to your input signal, as you see, the remainder matrix has the size of 1. So we cannot apply the level 4 to our input signal, and if you use the level 4 for your input signal, the Python print a warning for you that all of the value are border. So it was the result for level 1. If I change the level 1 to 2 and run again the code, as you see we have a 3 coefficient and the coefficient has the size 2. As you see here, the size of the coefficient at the level 2 is 2, and if I change it to 3 and run again, you see that we have a 4 coefficient and the size of the coefficient is 1, 1, 2, and 4. And if you set the level to 4 and run again, you see the Python print a warning for you: level 4 is too high. Coefficient will experience boundary effect. So it is better to use another level for your wavelet transform. The first value in the coefficient is approximation coefficients array, and the following elements are CAD or detailed coefficients array. As you see here, when you put a higher level, the number of coefficient is increased too. So we can define, for example, for level 2, if you want to use it for some application, you can define new name for your coefficient. For example, here I use CR2 and CD2 and CD1. I change it to the lowercase, and coefficients. So you set a new name for your variable CR2 approximation coefficient and CD1 detailed coefficient. So we can use these coefficients in your application. Okay, in this section I want to discuss about the partial discrete wavelet transform data decomposition with the command down COEF. In the previous lecture we learned how to apply DWT to a signal. For example, in here it is our input signal. I apply the DB2 wavelet with zero padding, the mode of zero padding to this signal, and extract the CA and CAD. There is another method in this library that can extract these coefficient, but it has a option that we can select what of these two coefficient we need. If you need approximation coefficient, you set A in here, and if you need the detailed coefficient, you set D in here. Then it extracts for you the type of coefficient that you need. So if you set D in here, it is a detailed construction. And if you set A in here, approximation reconstruction is for at the type of your wavelet and the mode of your wavelet and the level of your wavelet. If I run this code and open the coefficient, you set A, and I open the CA in here. As you see, these two variables are similar to each other. They are same. And if I set D in here, save and run again the code, you see that these two are same again. It means that you can select what type of coefficient you need. The difference between this command and this command is at the end of this command. In here we can set the level. We can change the level to, if I run again, you see that the coefficient is not similar to previous one. So in this command you just can set the level of your decomposition. You can see the result of the composition at level 3. So if you need to set the level of your partial discrete wavelet transform decomposition, you use the down COF. But you want to apply the discrete wavelet transform at the level of 1, you use this and you have a 2 variable at the output. Then you select which one you want to use in the remainder of your Python code. Okay, in this section I want to speak about 2D forward and inverse discrete wavelet transform. In previous lecture we get familiar with one-dimensional wavelet transform. Our previous signal was one-dimensional signal, but in here I want to read a two-dimensional signal. One of the most common two-dimensional signals are images that is used in many applications. For example, removing noise from an image or feature extraction for pattern recognition. In here I read an image Python logo.png. I use the OpenCV library, import cv2 and cv2.imread, read an image from hardware. For applying the 2D discrete wavelet transform, we use DWT2 to represent here the 2D array or two-dimensional discrete wavelet transform. We the input image img, then the type of your wavelet or the wavelet object, it's a name string, or your wavelet object in the second input. If I run this code, you will see the coefficients. It is a coefficient of wavelet transform. The first input is the array 150 in 134. And the second is a tuple. This tuple is the detail of wavelet coefficients. The first, this is approximation coefficients. So for extracting and giving a name to this variable, I use this command. CA in here represent the approximation. CH represent the horizontal detail. CFB is a vertical detail, and D is a diagonal detail coefficients. After extracting the wavelet transform, we can use to the inverse discrete wavelet transform with this command IDWT duo. The input is a coefficient from the EV 2D discrete wavelet transform and the type of the wavelet. In the output we have a inverted image. If I run this code, as you see here, there is an image at the output. It is, the size of the image is similar to the input image, but the type of the variable is different. We just need to type conversion to convert this image output to the UINT8. UINT8 is a common format for image in computer or another programming language because it represents every pixel between 0 to 255. So it was a simple command for to forward and inverse discrete wavelet transform. But as you see before, in some application we need to change the level of our wavelet transform. For applying the change of the level in the wavelet transform, we use the wave decay 2 and wave recay 2. Wave decay 2 represent the 2D multi-level decomposition, and wave recay 2 represent the multi-level reconstruction, 2D multi-level reconstruction. For using the wave decay 2, this part of the code is similar to previous, and in here we just use the wave decay 2, input is the image, then the type of the wavelet and the mode. I use 0 in here. You can use another type of mode, and the level. I use level 1 in here for comparison with the previous one. When you use level 1, this command is similar to this command, and the output we can extract the coefficients in similar way, and for invert wavelet or reconstruction we use the wave recay 2. When I run this code, you can see that a coefficient is extracted, and there is a tuple. In this tuple you can see the extracted wavelet coefficient for level 1. Okay, it was for level 1. If I want to use the level 2, I write this code before. When you change the level 2, the number of your coefficients is increased, and you have access to level 1 and level 2 coefficient in the new variables. So if I run again the code, now the coefficient contained one array and two tuples. The first array was the approximation coefficient, and the second one, uh, third one is the coefficient at the first level or level 1, and the second is the coefficient at the level 2. So we have a 5 uh, array in this variable, so I use this command to extract the approximation coefficient, then the detail in horizontal in level 2 and vertical detail in level 2 and diagonal detail in level 2 and similar way in level 1. So when you use a higher level in wavelet decomposition, you have access to the lower level in the coefficients variables. After extracting the coefficient, we can use the wave reconstruction 2 for multi-level 2D discrete wavelet transform. The input is a coefficient. It is a extracted coefficient from wavelet decay 2 and the type of variable and your mode, and the output you have a image out. As you see, the size of input image and output image are similar to each other. It means that the wavelet decomposition and wavelet reconstruction work fine in here. Another note in here is that, as you see before, we can set one of these variable to noun and the program will work. But in here, this library don't support the noun variable for any of these coefficients. You cannot set, for example, ch2 to noun and run the code for reconstruction in 2D dimensional. So all of your variable must have a value, so you can use the wavelet reconstruction. In previous lecture, we learned how to use one-dimensional wavelet transform or two-dimensional wavelet transform. In this lecture, we want to learn how to apply n-dimensional discrete wavelet transform and forward and inverse discrete wavelet transform. In the previous code, I used 0 in here to just convert my input image as a gray level. In a gray level, we have a two-dimensional array as the image. But when an image is colorful, we have when you read your image, you have a RGB matrix in variables. As you see here, this matrix is a three-dimensional. I selected this as an input signal for n-dimensional discrete wavelet transform. I use the dt and n is here represent the n-dimensional wavelet transform. We apply image, then the type of wavelet, the output is the coefficients. Then I use the ITWN, it is the inverse discrete wavelet transform in the n-dimensional inverse discrete wavelet transform. And if I use this command, as you see here, it's work, and we use the wavelet transform and inverse wavelet transform in n dimension. But there is a very important note here about the extracted coefficient wavelet transform. The output is a dictionary. Dictionary is a type of variable in Python that has a key and value. The key is in here, as you see, and the value is in here. What is this key? As I said before, the input matrix is a three-dimensional. Three-dimensional means there is two matrix or array as the input signal. So in this toolbox, use this method to represent the approximation and detail coefficient for user, or represent the approximation coefficients, and D represents the detail coefficients. So when you have or triple or, it means or on the first dimension, or as a second means that approximation on the second dimension, and or at the end means that approximation coefficient on the third dimension. And you can see in here, for example, OOD. O means the approximation coefficient on first dimension, and approximation coefficient on the second dimension, and detail coefficient on the third dimension. And you can read all of them until the end. That DDD means that detail coefficient at the first dimension, detail coefficient at on the second dimension, and detail coefficient on the third dimension. It is important to note in here when you use the n-dimensional wavelet transform. So as we saw before, we can have a wave decomposition at the n level, n-dimensional inverse, n-dimensional multi-level, n-dimensional discrete wavelet transform. In here you can set the level. Just change the end of this command n. It means the n discrete n-dimensional discrete wavelet transform. The coefficient is extracted, and at the output, as you see, the extracted coefficient as the input come to the wave reconstruction in the n-dimensional, and the type of wavelet and the mode. If I run this code, as you see here, the image, the coefficient is extracted. The extracted coefficient in this has a different with the previous. The OOO is in here, and the other variable as in here. As you see, OO, there is no OO in here because OO is the first in here, and the other variables are in this variable as a dictionary. Okay, in this toolbox, in this library, there are some functions for handling discrete wavelet transform coefficients. These function help you to convert the coefficient from previous comment in this toolbox to an array. This array simplify your work for applying this array to another, for example, artificial neural network or other classifier. This function is cuffs to array. The output of the wavedeck or wavedeck 2 or wavedeck n comes to the input of this function, and it is converted to two variables. First variable is, if I run this code, as you see here, it is the output of wavedeck. You are familiar with this because you see it in the previous lecture. And we have an array in here. As you see, the array is a combination of this variable. As you see here, the first element 2.1, 2.1. Second 4.9, 4.9, 7.7, 7.7, 10.6, 10.6, and the other is coming down of this variable. So this variable is very good for feature, for example, feature extraction or other purpose that you want to use wavelet transform. And coefficient slice is another variable, and this variable help you to because when you extract your array, sometimes you need to apply some function to it, for example, to remove the negative value or apply some thresholding to this array. After that, you need to convert the array to coefficients. This function helps you to convert the arrays to coefficients. You must specify in here what type of wavelet function did you use for calculating the wavelet coefficients. As you see here, I'm using wavedeck, so I use in here output format is wavedeck. So the output of we have a coefficient from array, and I apply the wave reconstruction at the end of this code to convert the coefficient to the to have inverse wavelet transform from this coefficient. So if you want to have a vector or array from your wavelet coefficients, you can use the coefficients to array. This function helps you to arranging a wavelet coefficient list into a single array. In some application, you need to convert your wavelet coefficient in a single array. Single array helps you. This, as you see here, for one-dimensional wavelet transform, it is very simple, but for n-dimensional, as you see before, we have a dictionary variable at output, and handling dictionary variable is complex, but with using the cuffs to array, you can handle this complex text easily, and it extracts for you the wavelet coefficients in a single array. Then you can apply this to for your application. In this lecture, we want to learn how to extract the wavelet coefficients when there is a level in our wavelet transform. In previous lecture, as you see here, the level was 1, so we can use the cuffs underline to array and array to cuffs. But in here, there is a level in the we are using the level, so I cannot use the previous way. In this way I must use two new uh, command, ravel underline cuffs. This command used when you apply a level for your wavelet transform, and the output is an array in the single array that you can use for your application after, or you can change the array, for example, for removing noise or other application, and for returning to the previous coefficients we can use the unravel cuffs. As you see here, the three input array, cuffs slice, cuffs shapes are input, and the final command is output format is the wave deck n, and the pywt.waverec n that used for reconstruction the wavelet in an n-dimensional. If you run the code as you see here, the cam reconstruction output has a similar size, and the array variable has is a vector. The length of this vector is more than 26,000. So if you need to have a single array in your application, you can use the ravel coefficients if you use the level in your code. So for multi-level wavelet coefficients, you must use the ravel cuffs, and for unravel you use the unravel cuffs, but in the level 1 you use the cuffs to array and array to cuffs. In this section I want to discuss about the stationary wavelet transform. This Python package PyWavelet support stationary wavelet transform. There are three commands for using stationary wavelet transform in this library: stability, stability 2, stability n. As you see in previous lectures, we have a DWT, and for stationary wavelet transform, it is changed to stability. It is very similar to previous use of this library. It just needs to change the D. For example, here I have a vector and apply the wavelet db2 at the level 3, and the coefficient is 1 is extracted. Or I have an image in here, it's a two-dimensional, so I can use the stability 2, and then the coefficient 2 is extracted from this image for wavelet R at level 2. Or we can use the n-dimensional stationary wavelet transform with stability n command. As you see here, this stationary wavelet transform doesn't support mode. In previous lectures, we can use mode, for example, zero padding or symmetric, but in here we cannot use the mode in our wavelet transform. We just can set the type of wavelet and the number of levels. As you see here, it is very similar to previous lectures, so I just run the code to see the output. As you see, coefficient 1 is a one-dimensional stationary Wavelet transform. If I open it, as you see that at the level 3, there are 30 tuples in the output. If I open one of the tuples, as you see, the size of the coefficient is similar to the input signal. It's the most important note in stationary Wavelet transform that the length of the output coefficient is same with input signal. Input signal has a length of 8 and the extracted coefficient has a length of 8. Or it is for level 1, it is for level 2, and it is for level 3. As you see, the size of the extracted coefficient doesn't change in stationary Wavelet transform, but in previous lecture, as you saw in discrete Wavelet transform, the size of the coefficient is decreased at each level. But in here, the size of the extracted wavelet coefficients are same in each level. So if I open the extracted coefficient at the two-dimensional stationary Wavelet transform, coefficient 2, as you see here, it is a 2-tuple because it is in level 2. If I open one of the level, as you see, the first is the approximation coefficient. As you see, the size of this approximation coefficient is similar to the input image. Or if I open the detailed coefficient, as you see, the detailed coefficient are similar to the input image. So if you want to use it in your application, you need to extract feature from this array. For example, variance in the our columns or stationary STD or other measurements you must be applied to this array and use it in your application. Coefficient n for n-dimensional stationary Wavelet transform. If I open it, as you see, it is a dict. We are familiar with dict. I described it in the previous lectures. As you see, AA is for diamond 1 and for diamond 2, approximation coefficient. I described it before. As you see, the output of this is very similar to the DWTN, but the size of the extracted coefficient is similar to the input image. So if you want to use stationary Wavelet transform in your Python code, you can use it in this way. This library also supports inverse stationary Wavelet transform. It is enough to use the I at the beginning of your command. I stability, similar to previous command, can be used for inverse stationary Wavelet transform or for two-dimensional array. You can use ISWT2, and for n-dimensional wavelet stationary Wavelet transform, we can use the ISWTN. The input are coefficients from the previous stability coefficient as the input and the type of your wavelet transform. It is similar to previous command. I just run the code, and just for example, I open the Y1. Y1 is the output from inverse stationary Wavelet transform in one-dimensional. If I open Y1 as you see, the value of the Y1 is similar to the input signal X, as you see here. are using the station wavelet transform, you can use this command in your Python code. In this section, I want to speak about the continuous wavelet transform. This library supports one-dimensional continuous wavelet transform. You can use this command in this way:ywt.cwt. CWT is abbreviation of continuous wavelet transform, and the first input is your data, then your scale. This define the wavelet scale to use, and third input is the name of your wavelet or a wavelet object, and the output are coefficients and frequencies. Coefficients and frequencies. Coefficients are these coefficients correspond to the scales that you define in your continuous wavelet transform. The coefficients are the coefficient of continuous wavelet transform of your input signal for the given scale and wavelet. And frequency are the frequency that your continuous wavelet transform is down. Forgetting that this package supports some type of continuous wavelet transform. To see them, I run this code, and in here you will see the variety of continuous wavelet transform that this library support. For example, CGIU1, CIGU2, see more FSP, Gaussian, the Gaussian 1, Mexican hat, or more one or more let, Shan or Shannon wavelet. All of these type of wavelet are continuous wavelet transform. To getting familiar with relation or formula of this wavelet transform, you can see the Mexican hat wavelet. In this package, it's represented by MEXH. The formula is this, or Morlet wavelet. The formula is it. As you see, it is a continuous. It is not discrete wavelet. And complex Morlet wavelet and Gaussian derivatives wavelet or Gauss P. P is integer between 1 and 8. As you see here, Gauss 1 to Gauss 8. So if you set P1, the P is fifth order derivatives of the function. When P is 1 is a 1 order derivatives of this function. So C Gaussian P can be 1 to 8, as you see here. C Gaussian 1 to C Gaussian 8. It's the formula. You must the fifth order derivative of this function. And Shannon is the relation of the Shannon wavelet. and the frequency B-spline wavelet. Okay, after getting familiar with continuous wavelet families, we'll learn um, how to apply continuous wavelet transform to our input signal. For creating a signal, I use the non-API NAP for creating arrays. X equal nap.arrange with 512. Then iterate, I define a equation for iterate. If I run this part of code, you can see the input signal that I define in here. I plot this. You will see it is a sinusoidal signal. I want to uh, I want to apply it and get the continuous wavelet transform. For this, I use the pywt.cwt, and the input is a y is our input signal, and the scale I want to calculate the continuous wavelet transform from 0 to 128, and the type of wavelet is Gaussian, as we see in the wavelet list. I can use Gaussian 1, and the output I have the coefficients and frequencies, and I show the coefficients with the math show from Plotlib. And if I run the code, you can see the coefficients extracted from input signal in continuous wavelet transform. You will see that it is a scale from 0 to 128, and it is the size of our input signal. Our size of our input signal was 512. So the size of this axis is 512, and the length of this axis is 128. Okay, for getting more familiar, I write another Python code. In this Python code, I use t as a input for our signal. Signal is a combination of two cosinus and exceptional and real. Exceptional and the real part of a complex vector. If I run the code, you can see I can show you the signal of input. You will see the signal of input in here. It is sinusoidal wave, not sinusoidal, but it has added with some signal to create a unharmonic signal. Then I define the scale. The scale in here is activity, the input signal, and the width, and the type of wavelet in here is the Mexican hat or MEXH. Output is the coefficients and frequency. I use this command to show the coefficient. If I run the code, you will see the lot of coefficient for getting better understanding of this output of continuous wavelet transfer. I show you the input signal. As you see in the input signal, when there is a change in the frequency of the signal, in the output we have a change in the spectrum of continuous wavelet transform. And there is a direct relationship between input signal and output from continuous wave transform. But in the previous one, because we have a symmetric input signal, our iterate was symmetric input signal. As you see here, uh, there is there is no change in the frequency input signal, and the output, the value of output of continuous Wavelet transform is symmetric too. So there is a direct relationship between your input signal and the output of your wavelet transform. So we can find that if there is some change in the frequency of input signal, the output of continuous wavelet transform will change too.